Our final speaker is Dr. Michael Pryce, who is a senior air system analyst working at the Defense Science and Technology Laboratory, providing operational analysis and decision support for future RAF acquisition program. And Dr. Pryce is also a member of the Royal Aeronautical Society. And today he will talk about the RAF policy and fighter design in the years 1945-1949.
Hello. Sorry I can't be with you today. I'd like to thank Harry Raffle and Paul Stoddart, who've organised this session for me remotely at short notice. I hope to join you for the Q&A afterwards. My name's Mike Pryce, and today I'll be talking about the Fall of Icarus, RAF policy and fighter design between 1945 and 1949. The heart of what I'm talking about today is that in this period, the RAF made some rapid changes to the changed situation brought about by atomic weapons. Those changes affected the subsequent history through the 50s and 60s, and I would say even up to today. They've both changed what the RAF does in terms of its missions, also the size of the force, also the size of the industry that we have in the UK now. So this period is a key one. Understanding it better, which in my case is something I'm still pursuing. Every time I open an archive box, as people will know, new things come out and new information. But I think it's been a poorly studied period in lots of ways. So I'm very interested and excited to be part of this event today and over the next couple of days, and to hear what other people have to say about this. In 1945, 1946, the RAF was a huge force. It was the biggest arm of the British Armed Forces, effectively, not in personnel perhaps, but certainly in terms of expenditure on equipment and in terms of the destructive effect it had on Germany in 1944, 1945, one of the most striking feats of arms of the 20th century. And what you see is that actually post-war is a very critical history that emerged, saying that actually the RAF, the British military in general, was anti-scientific, anti-technological, had been very slow at adapting to new technologies. There's well-known works by people like Corelli Barnett talking about this. And happily over the last couple of decades really, but the last 10, 15 years, people like David Edgerton have certainly focused on showing this to be essentially nonsense. What we see is, yes, the RAF was a scientific organisation. It was part of a huge military industrial complex, and the flypast, the VE Day flypast of 1946, showed just how dramatically large this force had become during the course of the war. During the course of the war, of course, there'd been other technological developments. Radar had come in before the war, the jet engine, the first jet aircraft had entered RAF service in 1944. But realistically, what won the war was old-fashioned traditional technology, piston-engined monoplane straight-wing aircraft, developed to almost to the limits of their capacity, but it was a huge effort. And there you see what certainly looked like Lancasters to me. There might be Lincolns flying past over London, and the air fleet that flew past in 1946 to celebrate the victory in Europe just was an immense one that no other nation apart from the United States could offer up. One of the important things is, when we're looking at this discussion, is we look back and we see the lack of science sometimes in aircraft design and in their use. And we think that perhaps things could have been done better. Perhaps we should have been more scientific. We should have had more radars and more jet engines involved. But actually, the decisions that were made during the war were very good ones. The early jet engine was considered more as a high altitude, response to high altitude reconnaissance threats by the Germans. There was no immediate need to have fast jet fighters in every role of mission. Jets had much shorter range, and actually as the war extended further into Europe, as the front line moved, having piston-engine aircraft made perfect sense. You could fly further with them. You could have a longer reach, which is one of the key aspects of air power. Operations during the Second World War as well had been affected by science. You had operational research coming along, led by people like Tizard, Patrick Blackett and others. And what they saw was actually by applying the scientific methods to operations, getting a feedback loop in terms of what works on the front line, what doesn't work, adjusting your tactics, adjusting your technology, but not necessarily going for big bang revolutionary technologies all the time. You would get the outcome you sought, victory. which is what they were celebrating in 1946. So this idea that science was lacking is a false one. But the science that was there was traditional science. It was the science where you analysed what existed and adjusted it, and then looked to see the effect of that adjustment to see if it was a positive or negative one, and then rinsed and repeated endlessly. That was military science. Aircraft themselves, where they were designed and tested scientifically, were built in the first instance before they were put into a wind tunnel off, and the whole aircraft would be put into a wind tunnel. Subscale wind tunnel models didn't work very well. The Spitfire was designed without the benefit of wind tunnel testing, because Reginald Mitchell had found that the previous design he'd come up with actually had not matched the wind tunnel predictions at all, because wind tunnels in the 1930s weren't terribly reliable. So you had a very mixed view of what science was, but it certainly wasn't lacking in 1945, 1946 for the RAF. Of course, the age of big science had arrived during the Second World War, and nothing made that clearer than the atomic bombs being dropped on Hiroshima and Nagasaki. And the destruction wrought was not actually, as many of you will know, as extensive as some of the more conventional raids, but the resources in terms of the air fleet required to deliver it was much less. So the atomic bomb completely changed the threat equation. If an enemy state could have atomic bombs, potentially they probably wouldn't be dropping tens of thousands of them and need thousands of aircraft to do that. But just a few getting through would radically alter what you needed to do, the consequences of a raid, and what you'd need to do to deal with a raid. And Fighter Command saw that very readily in 1945. They were not laggards and Luddites thinking, actually, this isn't an issue, we don't need to deal with it, only the Americans have got it. They immediately saw, if we're going to be one of the top nations, so to speak, we have to have the top weapon. And if we're going to have it, other nations may have it and may choose to use it against us. This was a clear assumption. And by November 1945, you had Air Marshal James Robb, who's the Commander-in-Chief of Fighter Command, an interesting character who had been a fighter pilot in the First World War, shooting down aircraft over the Western Front. Then he'd been involved in policing operations in Mesopotamia in the 1920s, training commands during the Second World War, and had in 1945 himself just learned to fly the Gloucester Meteor. So he was a jet fighter pilot. So he had been involved in the rapid technological change that had happened. And his view in his talk, named after the H.G. Wells book, The Shape of Things to Come, to the RAF Staff College in November 45, saw immediately that there was a fundamental issue. And that was, instead of thinking that shooting down 10% of an attacking force would be a good result, an outstanding result by the standards of the Second World War, you actually had to have 90% plus attrition of the enemy, potentially 100% if you possibly could. And the response to that was, well, what we need is new technology. We need radically new technology. It's striking how the technology came up with were effectively the same technologies we have today. If you sat down and did an air defense study today, you would come up with, for example, an airborne control unit to operate over the continent, as Rob wrote. Airborne warning and control system, AWACS. Whether he wanted 3, 5 or more it isn't clear, but certainly that idea of having airborne control to meet the threat further away from where you are was fundamental. He also saw a need for supersonic fighters, also stowed fighters, fighters that could loiter in the air for long periods of time, carried by parent aircraft, perhaps like some of the drone concepts we've got today of loyal wingmen and so on. It sounds almost like that. These would be under the control of that airborne control unit, and these fighter aircraft would be armed with long-range missiles, as he describes them, which include missiles as we understand them today, but also rockets, large shells with proximity fuses, and a range of other heavy-hitting weapons that could hopefully hit an atomic bomber and take it down immediately. So this vision of the future was there immediately after the atomic attacks, and the RAF worked quite quickly to implement this. One of the challenges they faced was that in 1946, in light of discoveries in Germany coming about through Operation Surgeon and other attempts, and Operation Paperclip by the Americans to understand what German technology was available, it was thought that actually if you're going to have a supersonic fighter, you couldn't have a straight-winged supersonic fighter, like the Miles M52 configuration that people discussed endlessly. It was cancelled in 1946. as a result of effectively German technology appearing to be better. There were issues with the Miles M52 to do with the air intake. One of the things I opened up a file and discovered, okay, there's a big discussion here, got to go through the technical details on that. But what was clear is that the view that the German approach to swept wing aircraft in particular to achieve high speed was a fundamental advance, and it was that would enable jet-powered supersonic flight. As part of these operations to get German technology, one of the key things was bringing back German designers and engineers to the UK. And one of the key people that the UK got was the chap you see on the slide here, Hans Multop, who came with his close associate, Martin Winter. And from their civil service records, it appears quite clear that perhaps Martin Winter was doing more of the work than Multop. He's certainly doing lots of the calculations and the sums, and was seen to be as capable as Multop. Well, Multop himself had been seen as being one of the key students of Ludwig Prandtl, the great aerodynamicist, the German aerodynamicist of the 20th century, who saw Hans Multop as his absolute best student he'd ever had. And a lot of Multop's work is still in use today. He's lots of his theoretical aerodynamic work. But during the war, he'd been a designer for the Focke-Wulf company. And you see him in this picture here holding his Huckebein design, which was a highly swept-wing fighter designed in 1944 for the Nazi emergency fighter program to meet fleets of American bombers, which in a sense, although it wasn't an atomic threat at the time, there was the potential for it to be that, was recognized it was going to be hugely destructive if you could not just deal with quite quickly with these bomber fleets. So in a sense, anticipating that atomic threat. And these high performance fighters were intended to leapfrog current fighters, to get literally to leapfrog the escorting Mustangs, but to have a higher level of technology to deal with the enemy threat. Hence the title of the slide, Das Bocksprung, German for the leapfrog. And this idea of leapfrogging technology was something that was brought with the Germans to the UK and implanted at the Royal Aircraft Establishment at Farnborough, where Multop arrived in 1947 along with Winter, quickly set to work designing a supersonic experimental aircraft, which essentially was an extension of his TA-183 Huckebein shown in the picture here, as he explains quite clearly in the report that he writes. This was picked up in early 1948 by what was called the Advanced Fighter Project Group at Farnborough, and their job was to propose a supersonic fighter, one that would meet the needs outlined by Rob to challenge the atomic threat of the future. If you have a high subsonic bomber, it was seen as an atomic weapon, you'd need a supersonic fighter to deal with it. And Multop's evangelical position was you needed high wing sweep for this. He was contemptuous of the delta wing, so it is only useful for experimental aircraft, and sold this idea quite heavily within the RAE. And by later 1948, what had happened was the RAE had taken Multop's work, extended it into a conceptual fighter with two or three engines stacked inside the fuselage and presented that to industry. And fundamentally, this was the configuration of what became the English Electric Lightning. The original concept was basically an extension of Multop's work at the RAE and then presented to the wider industry. There's an interesting aside around Multop. Going through his civil service records, you can see there was concerns that he was actually feeding information back to his former colleagues, Kurt Tank, the German designer who's now in Argentina. Multop's background, it certainly seems that he was quite a same aside in the Nazi probe in 1944, but he seemed to have no problem with that. There was some information I found on his father, who was very pro-Nazi, it seems, and actually there were some records sold recently on eBay which indicated that when the Nazis came to power, they his father had been censured under Weimar Germany as being too right-wing, and the Nazis sent him a letter saying, "Don't worry, you can't be too right-wing these days." So Multop's position seems to have been very much within the Nazi domain, and knowing what he did about what they were doing, it seems hard to believe that the censure and the sanction that the RAE were thinking of placing on him in light of the fact that he might possibly be feeding secrets to Kurt Tank was that perhaps some pressure could be applied by ceasing to provide them with season tickets for their daily journey to London, So take the train season ticket away from them. I can't believe that any hardened Nazi would respond too stridently to that. We wouldn't fear it too much. But what we saw was that within a year or so, that being written in 1949, Multop himself had moved to Germany, to America, sorry, to work for the Martin Aircraft Company, which was one of the options actually alongside taking away his season ticket. The others were send him to Imperial College or send him to America. But in that period, 1948 to 1949, Multop was working with English Electric. Freddie Page, the designer at English Electric, notes that there was a German whose ideas were given to us and that we worked on that subsequently. And it's a history that I'm uncovering still at the moment. Andrew Nahum has written quite a lot about this, but digging down underneath this, you can see that actually there is a lot more to be told. And it's quite interesting to see how this German model of design and approach, both in terms of the model aeroplane, you see the configuration, but also the scientific approach, the highly theoretical, analytical, aerodynamic approach, is something that was brought to Wharton thanks to the work of Multop at the RAE. There was a fundamental problem with Multop's belief in highly swept wings. And as I said earlier, the science of aircraft design was one where you build the airplane and then test it subsequently. And that probably wasn't going to be possible if you were going to get a supersonic aircraft. There was all sorts of failure modes, as we'd say these days, that the RAE identified. The aerodynamic problems could be solved by building a model aircraft, a full-scale model aircraft that replicated the shape of what became the Lightning, to test out the aerodynamics. But the biggest problem was seen as being the structural failures that might engender. And that required a whole new approach to the science of structures. Actually, oddly, in light of the fact that you had a Nazi involved in all this, the person who rode to the rescue in many ways was Alan Turing, whose design for the computer that became the Pilot Ace, built by the National Physical Laboratory, was first put to use dealing with the structural problems raised by this design configuration. A huge amount of effort went into this, pioneering aerodynamic work, stress calculations using a technique called the relaxation method. Talking to the designer who did much of this work before he passed away, it's quite clear this is something I'm deeply proud of. They felt that within the industry, English Electric or Wharton had established their credentials by doing this work, by making this design functional with the highly swept wing, by dealing with the structural problems that threw up. This effectively became a new way of designing airplanes, where you do lots of calculations in advance of building something, and that then made people feel much more comfortable with designing more advanced configurations, more radical configurations. But it did take time. This talk is about the period 1945 to 49, and what we saw was that although these initial designs were done, it was going to be many years before the Lightning entered service. There were lots of debates, even on the aerodynamics. On the slide there, it's got a tail. If we just flick back to that, one of Multop's big issues was a T-tail at the top of the fin, having the control surfaces there. There was lots of debates whether the English Electric Lightning should have this T-tail high up on the fin or have it low down on the fuselage. And that model aircraft, the short SB5, was built to test out these concepts alongside ones of affecting high wing sweep and aerodynamics. But the issues of high wing sweep and high speed still remained to be dealt with. They had to be calculated in advance using novel computing techniques at the time. Very, very radical change, but something the RAF fully supported. They thought, we need this supersonic fighter, so we need to do what has to be done to develop that supersonic fighter. And if that means creating a large scientific infrastructure and pioneering new techniques of computing, so be it. And some of that work started. The calculations using the relaxation method were done during 1949, and the Turing computer came in 1950, although planning work for it was being done during this period. But the RAF weren't done. They recognised, as the RAE did, that the highly swept wing concept of Multop was risky. They also went for a much more conventional fighter, what became the Hawker Hunter. And talking to the chap who designed some parts of the Hunter, and actually the key wing root structure on this slide for the SB5, where the wording, the wing is the thing, is where the corner of that box was the absolute location where all that calculation work was focused on the SB5. And a similar position on the Hunter actually took a hell of a lot less work. It didn't take a large team of people many years. It ended up taking one person a few weeks doing the work on their own, all the calculations, doing the drawings, issuing the drawings to the shops, and getting manufacturing going quite quickly. So the Lightning effectively was a contemporary of the Hawker Hunter, but it entered service much later. 2,000 Hunters had been built before the English Electric Lightning entered service. And of course, during the 1950s, the nuclear threat changed. It became more extensive. It also became seen as being carried by missiles, the famous Duncan Sands white paper. So aircraft like the Hawker Hunter, designed in this much simpler, non-scientific way, would be used for other missions. And it turned out that actually that simple approach led to more adaptable aircraft. The RAF has never shot down another aircraft using a supersonic platform since the Second World War. In fact, most of the active missions have always been ground attack. Certainly with the ones where ordnance have been released, they've all been ground attack in effect. So we have this situation where what was created in 1945 to 49 was a very radical scientific approach responding to the atomic threat. In 1960, when the Lightning entered service, they cost 4 times as much as the Hawker Hunters, which were still being built at that time. They had twice the performance. Was that good value? If you look at the Hawker Hunter, they were used for much longer than Lightning, used in many more missions. In fact, until recently, there were almost as many Hawker Hunters on the British military register still active as there were F-35B Lightning Joint Strike Fighters, because they're used for training missions still by contractors. So there is this issue that's raised by this period, which is we created an approach to designing and developing aeroplanes that basically was fit for purpose for an atomic threat, but was it actually fit for what subsequently happened? Is it fit today for what may happen in the future? The RAF has ended up with much more smaller fleets of aircraft, typically high performance, kind of on a performance graph, top right, whether that performance is speed or stealth and all those sorts of things. And that policy was established very firmly in that period after the atomic bomb. Understanding better the effects of that policy, as well as the causes and justifications of that policy, I think has a lot to contribute to today's debates and discussions around what we should do with the future force and how we could perhaps potentially rejuvenate the British aircraft industry, which there are attempts with Team Tempest and so on at the moment to get a new fighter into service. But is it following the right approach? Could there be another approach? On that note, I'll finish and say thank you and look forward to your questions later.